Today I'm here with Nigel Mounsey, who's the director of the DOE Joint Genome Institute, and Dr. Tamer Durrani, who's the lab's medical director. So thank you both for joining us today. I have some questions about the COVID variants, getting boosted, how the pandemic may continue to morph, if you don't mind. Nigel, can we start with you? I have a question for you on viruses. There seems to be nothing positive about them. So how do viruses fit into the natural world, and do they provide benefits to other organisms?
Yeah, it's a great question, Diane. Viruses really are everywhere, at least, where we've looked. And scientists estimate that there are about, 10 to the power of 31 individual viral particles inhabiting the oceans alone at any given time. And so that's, equivalent to more than around 10 billion times the estimated number of stars in the universe. So there's a heck of a lot of viruses out there. And not all of them are harmful, at least when you consider ecosystems. So, for example, in oceans, they lies microorganisms that lead to flooding of the food web with nutrients. Other viruses transfer genetic material between their hosts, and they give these host organisms new metabolic superpowers, allowing them to survive in otherwise inhospitable environments and contribute to things like nutrient cycling, which we're very interested in here at Berkeley Lab. But we're really still in the infancy of being able to identify viruses, and even less so in really understanding the roles they play.
Well, that's a number I'd like to see the zeros after that number of viruses that are out there. So there appear to be new variants cropping up every few months now. What do you know about the BA.2 variant or the stealth Omicron, and how do these variants relate to each other? Are they different from one another? And then kind of what type of challenges does that bring? How are they related? Where do they come from?
So the Coronaviridae family is characterized by this sort of relatively high replication fidelity. So it's kind of proofreading, right? And that's, compared to other viruses. And so I think we really hoped that SARS-CoV-2 evolution would be limited. But we now know, of course, that the virus is accumulating mutations more rapidly than we might have expected. And there's a sort of approximately 2 fixed mutations in the genome, happening every month now, and far higher rates of change happening in these more recent variants. So the speed of a viral pathogen evolution is not only dependent on the mutation rate, but also on the viral generation time, the duration of infection, number of variants that develop during infection, and the extent and selection of natural selection on the virus. So there's a lot of different factors that really, influence the rate of mutation. And we're all aware, of course, of Omicron, that seems to be spreading more easily than the original variant of COVID-19 and certainly the more recent Delta variant. But preliminary data, that we're getting in now suggests that Omicron really does cause more mild disease, although, some people may, of course, still get very severe disease, need hospitalization, and could die from infection from this variant. And so Omicron is distinct from other lineages. It has this remarkable number of mutations that are unusual. There are more than 50 mutations when compared to the original SARS-CoV-2 isolate from Wuhan, China, and some 30 of these contribute to changes in the amino acids in the spike protein, which is what the virus uses to attach to and fuse with cells, and that's the major target of neutralizing antibodies. So where did Omicron come from? Researchers have explained the emergence of previous variants through gradual evolution, where, as the virus replicates and transmits from person to person, random changes take place in the RNA sequence, some of which persist. But viruses can evolve faster, as I mentioned earlier, when there's selection pressure. And the sheer number and array of mutations are leading to researchers to postulate that Omicron did not result from the sort of more, typical person-to-person transmission, but evolved in a patient or a population that may have had chronic infection, or possibly through a person-to-animal, back-to-person spread. But there's no concrete evidence yet for either of these hypotheses. And as of today, Omicron is classified into the parental lineage, B1.1529, and 3 main sublineages, BA1, BA2, BA3, and there's also now a sublineage of BA1, BA1.1, just to confuse everybody. Although these are all considered Omicron variants, their sequences are really diversified. So for example, BA1 differs from BA2 by 50 amino acid changes, which is approximately twice as many as the number of amino acid differences between alpha, beta, gamma, and delta and the original SARS-CoV-2 isolate. BA2 is growing in dominance against BA1 background, and is now circulating in 69 countries globally. At the moment, though, the number of cases of BA2 in the US is relatively low at 3.9% of projected cases as of today, February 16th. And there is some early data that predicts that BA2 may be somewhat more transmissible than BA1, with the average transmission time for symptom onset being about half a day shorter for BA2 than BA1. But despite the significant differences between BA1 and BA2 in the virus spike protein, it does seem that vaccine efficacy is similar for BA1 and BA2, albeit at somewhat reduced levels against the original SARS-CoV-2 isolate. And BA2 also does appear to have some ability to escape neutralization by several monoclonal antibodies, but others do retain activity against BA2.
So what does this mean for me? If I've had the BA1 variant of the Omicron, will I get sick again with a different variant and the next variant as well? Is this going to continue?
Yeah, I mean, right now it's too early to tell if you get infected with, let's say, BA1, that you're going to get infected by BA2, because these variants are still, relatively new to the COVID-19 stage. But we've seen people be infected by one variant and then by a second variant at a later date, especially those that have not been vaccinated or those that have not received a booster in the sort of recommended time frame. And Tima will talk more about that in a minute. I would just reiterate, it's important that people get their vaccinations and boosters to provide immunity to emerging variants. And of course, just with Omicron, we really don't know what the next act will be with this virus.
So that brings us to another important question. Then, are there any research and development activities that may produce some vaccines that are more effective against several variants?
Yeah, as you might imagine, there are lots of activities happening now, and the teams that worked on the mRNA vaccines for SARS-CoV-2 are already turning their attention to the next generation of vaccines using the knowledge gained from the success of this first batch of vaccines. And so Moderna's already announced plans for multivalent vaccines against multiple SARS-CoV-2 variants, and also has a combination flu and COVID-19 vaccine, which will hopefully enter clinical trials later this year. Others are looking at chimeric mRNA vaccines that build on the modular nature of the coronavirus S protein, so using different combinations of S protein domains, and they've been able to raise antibodies in sort of lab studies against multiple coronaviruses. And another approach for broad vaccines is to vaccinate with virus-like particles. And these are proteins that self-assemble into a particle that's similar to a virus capsid, and which can display the domains of the SARS-CoV-2 spike protein to generate a multivalent mosaic virus-like particles for a range of variants. So lots of activity going on now, and some of these are starting to enter into phase 1, phase 2 trials.
Great, thank you. So, Dr. Durrani, let's talk about us as lab citizens. I think we're at rounded up to 98% vaccinated as a group against COVID, but we still are getting COVID cases at the lab. I think there were about 40 in January. Is the immunity that we've received from the original series, either the 2 doses of Moderna or Pfizer or 1 dose of J&J, are those gone?
No, the immunity's not gone. The vaccines were really designed with the goal to keep people from getting really ill, from having to go into the hospital or having to go into the ICU and things like that. So those were the initial outcome measures that were used when they were designing these. The immune system and the immunities remain, but it does go down over time. Sometimes you'll hear about immunity waning, and that just means it's going down over time. So the way we define these cases is kind of interesting because, we really define it by a test that is so specific, it can just pick a few strands of molecules that are put together. So although someone is testing positive, like we have people testing positive at the lab, they're not necessarily ill, or at least ill means they have to go to the hospital and things like that. And so from that perspective, we find it to be a win. They are still able to transmit the virus to others, but the more immunity that we gain, particularly from things like vaccines, it reduces the transmission from person to person, although it doesn't completely prevent it. So we have the immunity, but we still have the ability to transmit, and people still have the ability to get infected, although they really don't get that serious illness, at least not that we were seeing, pre-vaccine time.
So if these variants are going to continue to evolve, will we continue to need new boosters every few months?
Yeah, it's a good question. I don't think that anyone knows at this point. There's so many factors that go into this. It's hard to know. It's hard to give any predictions. I think most people who have made predictions around COVID have stopped at this point because it's just so hard to predict. So I think just time will tell. See if we need another booster.
Well, so we're talking about boosters. What is the immune response that you can expect after receiving a booster? And a kind of a follow-up to that, is the immune response different for those who acquired immunity through having had COVID versus those who've got it through a booster?
Yeah, so in general, when a person is exposed to a virus, their immune system is primed to learn that virus, and then they can respond to it in the future. And so as they get these exposures, the immune system starts to respond, and so you can measure that. And so the image that I've got on the screen shows that, after your first shot, you'll have, a level of immune response. After your second, it goes higher, and after your third, it goes higher. So the benefit of vaccines is that you know how much of the virus or portions of the virus someone's going to get exposed to. It's predictable, and you can time that out. Natural infection also improves immune response. The issues with natural infections, it's not always predictable. You're never quite sure if someone's just going to have a mild immune response or they're going to have a serious response that puts them in the hospital. And so that's why we tend to recommend the vaccine over natural infection. But people who've been both fully vaccinated and have had an infection tend to have the best immune response.
Nice to know. So what about timing of boosters? How long after my second dose if I had the 2-dose series, and how long after the first dose if I had the J&J?
So it's pretty complicated. So I'll tell it to you, and then we'll show a nice image that I think sort of explains this. But so it sort of breaks down into 3 categories, at least as recommended by the CDC. So for vaccines that were not FDA approved, but they are WHO approved, 6 months after completing your primary series is when you then can get your booster. For the Pfizer and Moderna vaccines, which are the mRNA-based vaccines, it's 5 months after completing. And for the Johnson & Johnson, it's 2 months after they're completing their initial shot. And so the image that you have in front of you shows that and gives some dates. So for example, if you received a non-FDA but a WHO-approved vaccine prior to August 1st, then you would receive your vaccine, up to 6 months later, which would be around the end of February. If it was after August 1st, then it's about 6 months after that date after August 1st. And so we have that both for the Pfizer, Moderna, and for the J&J vaccine.
All right, so we'll use the chart because that helps explain it as well. So question for you, Tamer, as a medical doctor and as an employee, what's the best way for us, both as lab employees and as global citizens, to move from the pandemic to what would be the endemic phase?
Yeah, it's a good question. I think first, I just want to make sure we all understand what we're talking about. So when we talk about a pandemic, the World Health Organization says, pandemic is something that's occurring worldwide or over a large geographic area, crossing international boundaries. And it's affecting a large number of people. And that's, we went from endemic to pandemic when this first started. And so when we're looking to go back to endemic, which is really just sort of the baseline, it doesn't mean this goes away. It just means it gets to a level that's, considered baseline and, relatively manageable from a public health standpoint. So I think, it'll be the way to get there. It's going to be a combination of having, people wherever they are and sort of on a global basis, having some immunity that allows the limitation of spread and limiting the severity of COVID. So whether that comes from ideally a sort of planned, predictable vaccination campaign or through natural immunity, either one will get us there. And between that and the time that gets us there is when we'll go back to this endemic phase, which will just be, it's not that it goes away, it's just that it's manageable within and, back to our baseline for our communities.
So that would be similar to what we go through every year with the flu?
Right. Yeah. And so when we have, we have sort of predictable respiratory viral season, which includes, the flu tends to be the one that's most predictable, sort of pre-COVID anyway, was most predictable. And we saw that cycle, just about starting around in the winter months and then ending, in spring. And it didn't mean that we didn't have flu the rest of the year. It's just we didn't see it at those levels. And so we will at some point get to that with COVID.
Great, thank you. So a question for both of you now. From your research perspective and from your clinical perspective, Nigel, why don't we start with you? What have you learned from in the past 2 years that has made you a better scientist?
Yeah, I mean, I think, what the pandemic's taught us is that science is so incredibly powerful, and that, we should trust the science, especially that's peer reviewed, and not be swayed by personal agendas or opinion. When we get time to catch our breath from this pandemic, there's really so much to reflect on. Our learnings on viral transmission and how to reduce the spread, the truly astonishing vaccine development, and for me as director of the JGI, the pivotal role genomics has played in all of this. It's really thrust science into the spotlight, and we should seize this opportunity to amplify our messages on the societal benefits of our work at the lab. And additionally, the pandemic's also shown the tremendous value that working in teams can have, and that breaking down, the silos between teams can deliver so much.
I agree with Nigel. I mean, I also think that there are so many basic tenets of public health that have been created and forgotten over time, and that we've seen them reinvigorated with this pandemic. We've seen a number of impressive breakthroughs, as Nigel talked about. We've also seen these sort of tried and true methods of disease prevention that have been very effective. So in some ways, a lot of us are very lucky to have never really experienced any type of public health emergency. But it's a reminder that humans have successfully dealt with this in the past, and we're likely to deal with it again in the future.
Well, thank you very much for being here today. I have opportunity here. Any last thoughts that you want to share with our audience?
No, I mean, I think, there's a lot of incredible science being done that will be done. We will learn a lot more. We'll increase our understanding, and, that will all play into how we continue to react to these types of emergencies and keep each other health and safety and support each other.
Yeah, I would say, I think we're just grateful for the people that we work with at the lab, and it's been a tremendous amount of strain for everybody. And I think, we've seen people do some really great things and have come together to help, get through this. And so I'm just grateful for that.
Well, thank you both for being here.
Thanks a lot.
Great. Thank you.